Hello, in this video I'd like to talk about complex systems. So a complex system consists of many interacting components. Sometimes these are called agents or particles. These interactions are often nonlinear. Complex systems exhibit emergent behavior over different scales and often self-organization over time. And we'll define what we mean by emergence and self-organization in a few minutes. Before we proceed, I'd like to give you a few examples. So on the cover of Science magazine a few years ago, there was this beautiful picture of a school of fish, and this is a complex system. So you can imagine that there's many individual interacting components, namely the fish, and there's emergent properties that come about as a result of these fish interacting with very localized rules, such as follow my neighbor to avoid predators, stay close but not too close, and things like that. We will study this sort of flocking behavior, swarming behavior later on in our course. Another sort of complex system that you might be well acquainted with is a social network. And so this picture on the right is a social network. This is actually from my research with Twitter reciprocal reply networks. Each dot in this picture is a person, and the dots, or the people, are connected if they've exhibited a reply to each other on a particular day using Twitter. So what emerges from all these localized interactions is this structural pattern, this social network. It evolves over time, it's self-organizing over time, and there's actually even some hierarchical structure. You see there's groups and groups within groups and things like that. We will study social networks more extensively as we proceed through our course. Okay, so let's define emergence. Emergence is a non-trivial relationship between the properties of a system at macroscopic and microscopic scales. So macroscopic properties are called emergent when it's hard to explain them from microscopic properties. Well, that's a lot of words for a very simple idea that the very localized interactions don't often give you a hint or give you a clue about what will happen at the larger scale. What's most important that you recognize here is that this is a property of scale, and I highly encourage you to go in and watch this video. It's from Nova Science Now. It's about emergence. It's 12 minutes long, and there's some excellent examples and visualizations of emergence. Next, I'd like to describe what we mean by self-organization. Self-organization is a dynamical process. It changes over time, right? It's a dynamical process by which a system spontaneously forms non-trivial macroscopic structures and or behaviors over time. So the key word here is time. Self-organization is a property that deals with temporal scale, so time, and the emergence deals with more spatial or problems of scale. There's a wonderful article about self-organization of ants. I highly encourage you to check that out. So where does complex systems lie within the bigger scope of problems that we work with in math, science, and engineering? Well, according to Weaver, there are two extreme ends of the spectrum. According to Weaver, there are problems of disorganized complexity. These problems are complex, but they're really disorganized. So if you think about random events like flipping a coin, you might get heads or tails, and that's just really random. It's well characterized by tools we have in probability and statistics. Not highly predictable, but we can characterize kind of over the long term what sorts of behaviors we expect. On the other end of the spectrum, we have problems of simplicity, and these problems are really don't have much randomness in them at all. They have very few degrees of freedom, things like classical mechanics. And over here, we've got known equations and theories, and we plug and chug our way through those sorts of things. Complex systems lie somewhere in the middle, and the idea here is that complex systems aren't totally random, right? There's enough structure so that things self-organize, but there is enough randomness that the properties can emerge that weren't there before. Lastly, as you read through section 1.2 in our textbook, you will be introduced to this beautiful visualization talking about complex systems, and again, emergence over scale, self-organization over time are really key themes. But there are 7 topical clusters, including collective behavior, networks, evolution and adaptation, pattern formation, systems theories, nonlinear dynamics, and game theory.